Hello everyone. In this video, I will talk about the basic physics terms, capacitors, dielectric, and capacitor plates. If you want to learn Maxwell's equation, special equation number 4, you should be able to understand these terms because they are very highly related to each other. You should know what capacitors is, what dielectrics are, and etc. All right, let's go ahead and get started. You see this diagram shows a battery connected in series with parallel plate capacitors. So this is the parallel plate, the capacitors. Here is one, and this is the second plate, the arrows showing it, and this whole thing called a capacitor. So if you don't have this capacitor, then it's just going to be one wire, a single wire is connected on both ends of battery. It constantly moves the current. So now we have this capacitor, and I'll explain you how does it work, and how does those electrons, those charges behave when we have this capacitor, and then at the end I will tell you why we're using this kind of capacitors, why we make these things complicated. So the battery's positive terminal is connected on one plate, and its negative terminal is connected to the other plate. You see here the positive. This is the positive terminal, and this is the negative terminal. So you see, these each are connected to directly to each plate of the capacitor. So now what? So in metallic wire or a metal capacitor, the movable charge carriers are electrons. So what it's running is the electrons. When the battery is connected, so its negative terminals or terminal, it pushes the electron or repels them into the wire towards the capacitor plate that's attached to it. And here we have the negative terminal. So this from negative terminal, the electron moves all the way until here. So I will just write E direction of the electrons. So this is how it works. So as you know, the electrons are negatively charged, and of course it will start these negative terminals try to push the electrons towards this capacitor, the plate, the negative plate of the capacitor. So so this excess electron accumulate on the plate, making it negatively charged, and that's why you see this negatively charged on the left side of the plate. And how about the positive charge? Why do we have the positive charge here on the other side, this positive charge on the other side of the plate? So here is the subtle but crucial point. The battery does not actually send positive particles to the other plate. Instead, what it does is it pulls the electrons off that plate connected to the positive terminal. So this plate, so this plate we have the right plate, from the right plate, this battery tries to pull the electrons towards itself. So these atoms in the metal still have their positively charged nuclei, but now there are fewer electrons than protons. So the plate as a whole becomes, that's why this whole positive, because as I said, instead when it pulls the electrons off the plate connected to its positive terminal, the plate left with a deficiency of electrons, and the atoms in the metal still have their positive charged nuclei, but now there are in fewer electrons than protons here. So the external wire provides the path so that electrons move around the circuit, leaving one capacitor plate and piling up on the other side. Inside the dielectric, so there is no any electron move here. And as you see here, please ignore so far this electric field that I wrote. I will gonna explain it just in a minute. So inside this capacitor, there is no any electron movement. So I'm just gonna write here no electron move. That's the reason why we have here capacitor. Otherwise, we wouldn't need all these. They would just straightly draw a line there. So there is no any electron move. It's an insulator. But the electric field across it forms instantly as soon as charge builds up on the plates. The dielectric itself does not have free electrons to conduct current. However, its molecules are polarizable. So now what's polarizable? So applied electric field slightly shifts the positive and negative parts of each molecule in opposite direction. That's why you see here it shifts this the positive charges are here piled up and negative charges are here and piled up on the right side of the plate, and this is called polarization, and that internal is called rearrangement that reduce the overall field or net field within this dielectric, and that allows capacitor to store more and more charge at the same voltage. So the charges are keep coming and they keep piling up, so negative from here and then positive from um, negative from here and then positive from here. So they keep piling those charges across the plate, and due to those rearrangements it reduces the overall field, and then the more and more electrons more charges will be stored. So not just electrons but charges, because they're plus and minus charge there. So the capacitor to store more charge at the same voltage. So why current moves opposite direction? And now let's talk about this we call elephant in the room. So you see here, I didn't just put these arrows here, and you see the arrows pointing coming from the positive side all the way to the negative side of the battery. So if the electron's direction is from negative to positive, so here I have, so I just again gonna write all this electron direction. So then why we have here these blue arrows, and why the actual current, not the electron, current is from positive to negative. So the thing is here, when the idea of electric current was first defined, so that was way before the electrons were discovered. So electrons were discovered after the current was discovered. So that's why scientists simply decided that current would mean the flow of positive charge, and that convention stuck. So by the definition, conventional current flows in the direction of a positive charge, would move from the battery's positive terminal to its negative terminal. We just stick with the scientists what they said early years. So that's why it's just accepted. So I apologize for that, but again, the current, when you say the current, this is the flow of I'm just gonna write current direction, and the other arrows, that's the direction of electrons, how electrons move. So we'll just assume that the current is moving from positive to negative, just like it's indicated with a blue arrows. So now let's talk about this capacitor. What's this capacitor? So I just mentioned it, that yeah, it stores the charge there. It's due to rearrangement, etc. But let's just go a little bit deeper with that. So you have two metal plates separated by insulating materials here. They're called dielectric material. I wrote it down there. When you connect the battery, electrons start flowing in the external circuit. They pile up on the negative plate and then are pulled off the positive plate, just like I explained a few minutes ago. But inside the capacitor gaps, the dielectric prevents, as I mentioned, electrons from actually crossing over. So how can we still talk about the current flowing through this whole circuit if the middle of it's blocked? There is a dielectric material, so it's conduction. There is no conduction. So the thing is, even though there is no electron that moves from So here I'm just gonna write again no electrons. I know I wrote it down here, but I'm just gonna write it on the top also. Even though there is no any electrons that move through this dielectric, something else changing inside it, and that's we call it electric field. That's why I have here written the electric field, and that's the direction of the electric field here. As the charge accumulates on the plate, that field between these two, it grows very strong, and that changing the electric field actually acts almost like a bridge. So that's why I have here blue arrows and an effect of current through the gap. So this idea formalized in Maxwell's equation, where he introduced a new term called displacement current. So again, so this is now a displacement current. So I'm just gonna draw arrow here, and I'm gonna write this is displacement current. Okay, so what about this, the blue arrows now? What kind of current they are? So these currents are called conduction current or conducting current. So I'm just gonna write conduction current. Okay, current. So now we have two currents. The conduction current that goes through the wires, as it's indicated with blue arrows. Now we have also displacement current, which is current that's going in within this dielectric material. So two different. That was introduced by Maxwell. So it's not a current of moving charge, but a current associated with the changing this electric field. So this electric field inside this, it keep changing. So the question is, who cares? Why do we have to complicate all these terms and bringing the capacitor, dielectrics, and everything, and then keeping this electric field inside this material? So it's this dielectric and capacitor system isn't just this classroom example. It's one of the most essential component in every modern physics, electrical and electronic devices. So whether you have a stabilizing voltage, whether it's stabilizing voltage, it's storing energy, it's tuning radio waves or filtering noises. So it's always the same principle. We call it storing the energy in an electric field across this dielectric. So store energy storage. So we do need this dielectric to store the energy. So I'm just gonna write here this stores the energy, or we call it stores an electric field. Okay. So after watching this video, I'll highly recommend you to watch the Maxwell's force equation that I'm going to upload right now. And with that, I will conclude with my video, and also in my next video, I'll conclude the force equation, the last equation